a good resource available for anyone doing research, especially within the university community, graduate students, undergraduates, postdoctorate researchers, and even faculty use the facility. So for those of you who are not aware of the location of our facility, we're on the first floor of the North Engineering Building. It's in the northeast corner of the building, right across the hall from where the engineering technology offices are located. The room number itself for the main lab is 1496, but we also have a few adjacent labs that are part of the facility as well. All right. So just a little bit about the background. CMSC was established in 2009 with some funding from a few different agencies, over $3 million worth of investment, and it's probably increased from that in the years afterwards total. It's a core level facility of the university, so it means that we're not specifically one part of any department. We fall under the purview of the College of Engineering as well, but we offer our equipment and facilities and services for use for anyone within the College of Engineering, also from natural sciences and mathematics, health science, medical campus come use facilities. And also we have quite a bit of external users from nearby universities that come to use the location. So local ones such as BGSU, but we even have farther away like University of Michigan, Ohio State, and others that come to use it as well. Professionally managed, so we have a staff currently 3 full-time scientists dedicated to operating the facility. And basically we not only provide the equipment for use, but also our time and expertise for specific questions, but also we can collaborate on larger projects as needed. So as you see, we've got a lot of different partners and outside users that come to use it. And because of that, we have a very wide range of expertise and disciplines that kind of combine together. So it's not as though we are limited to any one particular material system or characterization method. It's more generalized that we try to provide our services and capabilities. So as I'm sure all of you are aware, characterization is a critical aspect of performing research. So you need to not only be able to understand the work that you've done in your research and characterize your materials and methods through that, but then it's part of the actual process of going back and reiterating that examination process and trying to understand the clear conclusions that come out of that. So we do everything from nanoscale level all the way up to macro scale characterization here. We have a wide range of different capabilities, and we're going to cover those in more detail. And that's something that we want to make sure is available to use by the students themselves as an educational purpose, but also by the researchers in order to advance their scientific goals. So, and it's just going a little bit over that. It's not only the technical gritty details, if you will, about individual sample characteristics, but also even on a higher level trying to understand macro scale features, more complex phenomena such as failure analysis. That's a good example, to where there's often many different convoluted mechanisms going on, and so understanding all of those holistically as well as independently, that's something that's important. All right, so getting into some of the more specific details about what's available at CMSC. So we've got a wide range of instrumentation, and this is not necessarily all-inclusive. There's a number of other facilities that we have available, and it seems like every year we're trying to add more capabilities to enhance the this list of equipment and operations available to the researchers. But our core offering for the metrology, so we have our suite of electron microscopes. So we have traditional scanning electron microscopes that can do magnifications of up to maybe 500,000x, good for looking at soft materials, polymers, biomaterials, metals, ceramics. thin films, large substrates, can examine that. We also have transmission electron microscopy, which can look at nanomaterials and thin foil sections of larger substrates. And that can go up to much higher magnifications, typically on the order of several million X. So you're looking at individual atoms at that point, or orientations of small crystals. We have focused ion beam, which is both a characteristic method, but it's also a sample preparation method, and we'll go a little bit of detail about that. Atomic force microscopy, we have an environmental scanning electron microscope, so that's something convenient for looking at samples that you need just rough vacuum, that maybe you don't want to completely desiccate them, so maybe gels or biological cells. Optical microscopy, we have several options of that. Electron backscatter diffraction, that's a capability that we have as part of one of our SEMs. Spectroscopy, so we have Fourier transform infrared spectroscopy. That's convenient for looking at organic compounds and chemical bonding, identifying specific, say, functional groups in a material and trying to identify materials that way, or changes in materials. Raman spectroscopy, so that's another one that uses optical light laser to basically probe structural characterization of material. We also have UV-vis spectroscopy, so looking at, say, optical absorbance in materials, trying to understand, say, coloration of materials. EDS, that's an energy dispersive X-ray spectroscopy, so that's a part of the suite of the SEM actually, but it's using the high energy of the electrons bombarding the sample to then cause the material to fluoresce and understand the elemental composition of that material. So liquid chromatography, MS, so basically using a chromatography column to separate out liquids and identifying specific organic substances within a material. Inductively coupled plasma mass spectroscopy, so that's breaking down a material into its constituent atoms and determining the elemental composition, and that is something that is sensitive in some cases all the way down to parts per million or parts per billion of certain elements. Gas chromatography mass spec, so looking at samples that are either gaseous or that can be easily evaporated and then separating them out into the respective species, identifying them. GPC, gel permeation chromatography, so say you've got mixtures of long chain molecules like polymers or other organic compounds, trying to separate them out and determine their respective sizes. Carbon, hydrogen, nitrogen, oxygen analyzer for looking at organic compounds and getting accurate measurements of those light elements that maybe aren't very responsive to techniques such as EDS. Thermal analysis, so we've got the standard differential scanning calorimetry, understanding the energetics that go on with, say, phase transitions and second order transitions in materials. That's using heat flow. We also have the ability to do modulation of that. So if you want to get greater understanding of characteristics such as heat capacity, thermal conductivity, things of that nature, separating out thermodynamic effects from kinetic effects within a material, that's where the modulation comes into play. Thermogravimetric analysis, so basically understanding how samples can change their weight as a function of heat and environment. So looking at things such as evaporation of samples, thermal decomposition of samples, oxidation paralysis, and it can be gains as well. So let's say you're trying to purposely oxidize a sample, or you can use a reducing environment and reduce that, so you can see the effects of that. SDT at the end there, that's actually sequential DSC and TJ measurements, so there's capability of doing both simultaneously. And then DMA, dynamic mechanical analysis, so that's something that you can actually use both temperature and mechanical stress, strain, frequency perturbations, a number of things to determine properties of the material that way. X-ray analysis, so we've got a system that can do combined X-ray diffraction and small angle X-ray scattering. So the former is more for structural characterization, the latter is for more size and distribution characterization. We'll get into that. And then we have a range of other supporting equipment for doing different characterizations, and as well as a lot of equipment for different sample preparations. And so we'll cover some of that in detail as well. And by all means, if anyone has any questions at all, feel free. You can interrupt during or save the questions to the end. Either way is fine with me. So some examples of the SEM characterizations. So because the SEM has the ability to look at electrons, not only the primary electrons that are interacting with the sample directly and then being deflected off, but also secondary electrons that are being emitted from the sample. You can look at a wide range of contrasts and characteristics. So you can tweak the detectors to try to be more focused on surface topography. So for example, in the image in the center there, you're seeing some organic beads. It's chitosan material on the surface, and you can see very clearly what's present. Or you can change the energy and detector settings to be more interested in phases for, say, samples that may be polished and you don't have a lot of difference in topography, to where you can get those highlighted of different compositions, and then you can support that with some of the elemental analysis capabilities. So you can do maps and you can see where the distributions are of certain elements, and then you can also do quantitative analysis, so you can get high accuracy measurements of the actual composition ratios in terms of weight or atomic percent at those capabilities. So some other examples of what was going on. So this was a characterization that was done of some cardiac stents, looking at drug coatings, I believe it was, on the surface of those stent materials. So, and then just a little more description about the one of our microscopes as well, just the emission, the different detectors that were associated with it. This one here specifically, it's just got a small sample exchange load lock, so it's meant for smaller samples for relatively high-end, high magnification analysis. So some other examples from SEM, more specific to metal analysis. So you can do a wide range of things. So you can look at fracture analysis. So for example, if you've got a fracture surface and you want to see, say, where the crack initiation and propagation occurred, you can see that. If you've got fatigue, you can typically see like the beach mark characteristics of that. If you want to examine, say, localized effects from doing nano indentation measurements, you can look at some of that. This one down here, this was actually using our ion beam to do some localized polishing, and that revealed some of the local characteristics of the different crystalline domains that were there. Other things you can do, so this center one here, this is an example of an alloy that had some different phases form in different precipitation regions. So you can see where some of these grains are the highly interlaminated layers of like a pearlitic or similar structure or bainite, and other areas are where they're more homogeneous and didn't have that phase separation, and you can definitely clearly see regions of grain boundaries. And then you can look at orientation. So these two images are actually from the same sample of different orientations to see how some of these precipitates are distributed, and also to see how, say, working the sample has changed the morphology in different directions. So this was in the longitudinal direction cross-section. This is in a transverse cross-section. So all of that is characterizations that can be accomplished with the SEM only. So another instrument is the scanning transmission electron microscope. So it's very similar in terms of using an electron beam to probe the sample, but this one uses a much higher energy, whereas the previous microscope, typically the maximum energy is around 30 kilo electron volts of energy. This one here goes up to 200 kV, and to where the beam is actually powerful enough that it can actually pass through the entire sample. We typically deal with thin samples or nanomaterials. But basically you can get images of particles, so you can see that these are nanospheres of materials or microspheres that were examined. You can see the thickness and you can see the information there. Contrast of gold particles, you can actually, if you get proper samples, you can look at individual lattice planes and even individual atoms within the lattice, looking at those information. And also this has the same type of elemental detector as the SEM, so you can again look at your two-dimensional distribution of your elements, as well as doing quantitative analysis. And then just some other examples from this instrument. So you can see, looking at some of these spheres, so this is I think there was a metal microparticle that had some coatings on the outside, so you can examine the actual topology and effective thickness of some of these coatings on the sample of the surface. So by using the higher energy, that 200 kV, it provides higher resolution So you can get information down to much finer detail than you, say, could with a typical SEM. And so another microparticle or submicron particle that you're just examining information on. You can also use the ion beam to prepare foils of samples. So you say you can do cutouts of, say, metal samples, ceramics, laminated samples. You can do a number of analysis with that, and then using the TEM you can look at different image. So this is a metal alloy sample that you can see clearly. You've got regions of differing phase composition there, and almost like a dendrite or root system going through there. This is an example of actually that previous metal sample that had the different regions of phases. So you can see on the right, it's very homogeneous. You don't see any significant differences in there. And then right across the grain boundary, you've got regions to where you've got phase segregation going on, and you can see the individual lamina of each of these phases being present, and you can analyze size, distribution, elemental information for those different features, as well as examining what's going on at the grain boundaries themselves. And you can even look at higher details. So on another metal sample, so this is a region of kind of lower magnification, so 20,000x, that you can see different regions. You can see some of the phase boundaries, but if you go to even higher magnification, you can start to see nanoscale precipitates forming within that, and you can get characterizations of those as well. And then we touched a little bit about this, so this focus ion beam. So on one of our scopes that is an SEM that can do everything that we've already discussed, it also has another column installed. So instead of using electrons to bombard the sample, it uses a beam of controlled gallium metal ions. So because of that, you can use it for imaging, even though it's somewhat destructive, but you can also use it to manipulate your samples. So you can use it in a gentle way to do some of the polishing on the surface locally, like I showed you in the one of that previous image. But you can also use it to actually prepare samples and do other kinds of microscopic machining. So this is an example of how to use that instrument to prepare one of those thin foils for TEM analysis. Eventually, you basically cut it, remove it out, put it on a grid, and then you can put it in the TEM and analyze it. But you can also use that to do other things. So this is an example of a material that had some heavy surface corrosion, and we wanted to examine what was actually going on to the surface itself. And so using the ion beam, we identified a region of interest and basically cut away part of it locally so we can get a cross section, and then we could actually image what was going on in terms of the localized effects of the corrosion, and see using the EDS and other information, we could actually analyze the composition of these different layers, how the elements were moving when they were exposed to the corrosive fluid, and so on and so forth. So there's quite a bit of range that can be done with this suite of electron microscopes. And then one other relatively recently added capability is that we have an electron backscatter detector that can be used on specially highly polished samples to essentially identify the crystallographic domain and orientation of individual grains. So essentially it's got just this detector at it. The detector itself can be used for imaging directly, or it can use the electron beams bombarding the particles. When each electron beam hits an individual particle, it has this three-dimensional diffraction phenomenon going on. And basically this detector here analyzes that. It's called a Kikuchi pattern for each individual crystallite. And then by using some fitting to some known databases of crystallographic information, it can assign a specific phase and orientation to every crystal that it can accurately analyze on that sample, and then provide a two-dimensional map like that. And then you can get information from that map, such as overall sample orientation, pole figures, information about grain boundaries, how coherent they are, things of that nature. So that detector was actually, we had to send it back for some repairs, so it's on its way back. We're hoping to have that installed and ready to use in the next 2 weeks or so. And so that'll be a capability that's back again. And then also using that same instrument with the FIB and the EBSD, it also has the capability of doing environmental SEM. So essentially, that's a way that we can do at a much lower intensity vacuum than, say, the other microscopes. We can independently control the pressure and relative humidity within the chamber itself, and we also have a cooling stage that you can control the temperature of the sample. And so you can do a number of things such as real-time condensation measurements or controlled measurements of live biological samples or gels or other things to where you don't want to have them purely desiccated out. And so these are, this is a little video, will it play? Yes, it will. So you can see that was a real-time change as a function of changing the humidity and the temperature of what was going on in the sample. So that video was recorded in the instrument as well. You can see it was heating again. Yep. So you can see that it recrystallizes as the humidity changes. And then this was a organic sample, and this was a screw from a biological implant to analyze some of the contaminants on there, as well as some of the growth that occurred on top of that. So, okay. So aside from our electron microscopes, we've got a suite of other characterizations. So one of them is atomic force microscopy. So this is another technique that's convenient for looking at surface topography, so you can get information such as roughness. You can also look at phase information on the sample. This requires very flat surfaces, so your surface roughness typically can't be more than just a few microns, but it has sensitivity all the way down to a fraction of a nanometer in terms of the vertical resolution. So it can be very convenient to use, and in theory you could use it on dry samples or within a fluid as well. And then the X-ray capability. So we have a Rigaku diffractometer that can be operated in two modes. So one of them is the X-ray diffraction capability. So basically, by using geometric diffraction, which is essentially long-range scattering to where you've got constructive and destructive interference effects occurring, you can use the information obtained by the intensity and angle of the scattered X-rays to effectively back calculate the crystal size, crystal orientation, structure of materials, identify often if the individual phase of interest, including several phases. If it's an amorphous material, you can get information on whether it's amorphous and some of the degree of the short order of that material as well. Texture orientation, so that's kind of similar to the pole figures that were generated in the EBSD, but this is a more of a bulk technique that you can determine what is the relative overall degree of orientation of those crystals, or are they just randomized. You can get information about that. You can also get some information about the strain and stress, or the strain upon the crystals as well, to see if it's something that's deviated from a natural random. Characterized polymorphs, so not only do we have the ability to do the measurements, but we've got a dedicated piece of software to analyze that data. So this is an example of a mixture of two different phases of titanium dioxide, and then just using the XRD, it was able to identify not only that both phases were present, but give the concentrations of those respective phases. So something to where there is no chemical difference between them, but it's all structure. And then aside from the diffraction, it also has the ability to operate in the small angle X-ray scattering mode. So this is a mode that is typically used when you've got a material that has a matrix phase and an inclusion phase, and you've got some significant contrast in terms of density or scattering features of those phases. Now, what does that mean? That could be something as simple as, say, a polymer foam, to where you've just got void spaces inside of the matrix. It could be, let's say, a polymer that you've added some materials to as an additive to change the properties. So, say, graphene or carbon nanotubes or organic or inorganic ceramic particles in there. It could be something, basically anything to where you've got a distribution and you want to understand information about, say, what is the average size of those particles? What is their distribution? What is, say, how well agglomerated are they, or are they very well distributed? So basically you can use that scattering, and by sweeping the angle of the scattered pattern, you can get information about that, and then you apply different mathematical models to it to extract the data of interest that you need. So all of that is capable with one instrument. And some different optical type of spectroscopy. So we have FTIR capability. So again, this basically uses light that starts from the near infrared all the way down into the mid and long range infrared to basically understand some of the interactions with material that will yield information about chemical bonding. So things like metals and glasses are not necessarily going to be very active, but organics and some semiconductors and ceramic materials will definitely be able to give a lot of these strong responses. So you can get information not only on individual chemical groups, but often you can get enough information to fully identify materials of interest and actually analyze whether it's a mixture of two or more different materials and get approximate information on the relative amounts of those mixtures. Raman spectroscopy, so basically that's another one that it's somewhat complementary to the XRD, but instead of using diffraction to get structural information, it uses vibrational spectroscopy within the material to understand both some information about local and long-range order. UV-vis spectrophotometer, that's not pictured here, but basically that's one to where you have light that ranges from the UV all the way to the near IR, and it sweeps through that spectrum, and then you can analyze about how it interacts with your material. So whether it's a solid material like a film and you're just trying to see the light transmit through it, or let's say you've got a solution or a colloid particle or something like that, and you want to understand how it absorbs the light, you can understand that information as well. And then this ICP-MS down here, so that's another one that you will basically take a sample. It's intended for liquid samples, but if you have a solid, then we have the capability most times of being able to digest that in an appropriate solution. And then once we've got your sample dissolved, then basically we'll analyze it, and this provides elemental information. Now the difference between this instrument and say the EDS that we covered earlier, the EDS has limits of detection typically on the order of about 0.1%, and then even accuracy at about 0.5% or greater. That's when you start to get out of the noise of that. With the ICP-MS, it is best used for looking at trace level analysis. So let's say you've got, say, a metal that has trace level of different elements in it that maybe are there intentionally or unintentionally, and you want to analyze that. You can use this instrument to perform that characterization and understand some of the finer contents of that. Also, if you've got a bulk material and you want to make sure you've got the most representative composition for that entire material, this has the advantage that you can take the entire sample, digest it, and then dilute it and get an accurate concentration that way. Whereas the EDS technique, it's only going to show you locally wherever you were viewing with the electron beam itself. So it may or may not be representative of the true bulk sample. All right. So there's some more information about the Raman spectroscopy, just an example that was used for looking at some collagen cross-linking on a bone. So that might not be as useful here. So FTIR, one of the other FTIR scopes we've got, it's an imaging system. So this has the capability of doing two-dimensional analysis of the FTIR, so you can actually create two-dimensional maps of samples of interest and see different effective compositions between them and try to understand different effects about what's going on. So it's not only for looking at cross-sections of samples, say like pharmaceutical pills that you might want to see how evenly distributed drugs are, but you can also look at cross-sections of, say, laminates, like polymer coatings that may have 3, 4, up to 10 different layers on that, and they're so close together that you might need a better way to distinguish the individual layers there. Yep, so there's another example of doing this layer analysis on a polymer. So the one thing about preparing samples for this imaging system, again, it has to be something that's very cleanly polished, very smooth surface, so that you get excellent contact with the surface and you get the best optical response from it. All right, this is another instrument that we have, surface plasmon resonance. So basically this is just looking at, say, for protein analysis or other kind of organic compounds on surfaces. So if you're doing something that you're interested in having it exposed to biological tissue or biological fluid, and you want to understand how that might interact with the surface of your particular device, then this is something useful for analyzing that material surface. So liquid chromatography. So again, this is something that we use to typically separate out and identify different organic components within a mixture. So that's something that basically runs the sample through a column. The column separates it out, and then this mass spectrometer in the end, similar to the ICP in terms of how it analyzes, but the difference is the ICP is only for elements, because it essentially has a high energy method of breaking down the sample upon submission into the instrument, that it fully ionizes. So everything is blown apart. But this one, it's much lower energy. It really doesn't damage any of the materials as they're being separated. And then only when it goes to the analyzer, then it's destructive, but in a way to actually understand the size and relative contributions to the organic part of the sample. Okay, so we have a suite of thermal analysis equipment as well. So we actually have two different differential scanning calorimeters, and basically those are for analyzing energetic transitions within a sample that would have some kind of endothermic or exothermic response. So that could be melting, it could be crystallization, it could be glass transitions, it could be some other second order transitions, such as Curie points or things of that nature. So basically anything to where the transition in your sample is involving some kind of delta H. This is something, one of the techniques that you can use to analyze it. And it can be done by default. We've got it set up. It can be run in air or inert nitrogen, but it does have the capability of having other environments used depending on the situation. And so you can pull out those information about the samples. And then we also have a thermogravimetric analyzer. Basically, it's just, if you want to look at stability, if you want to look at decomposition, moisture loss, or if you're doing, say, epoxy studies and you want to see how the curing of your epoxy goes. This is another convenient method of using it. But instead of analyzing the change in energy between the sample, it's just looking at weight alone. Right? And then, I should also mention that there's another instrument that actually kind of combines both the capabilities of the DSC and the TGA together. And we're just getting that up online, and that should be available soon for anyone to use as well. So this is an interesting piece of equipment. This is a dynamic mechanical analyzer. So basically, it has the ability of performing mechanical measurements, simple mechanical measurements on samples such as tensile studies, compression studies, dual cantilever bending, three-point bending. There's a wide range of different types of material clamps that can be installed on this to basically perform the test. Now, it doesn't apply high forces like you would see on like an Instron tensile test system. But basically what it can do is that you can not only vary the time and intensity of the forces, but you can add perturbations and oscillations into it. And you can also do this under a very wide range of temperatures. I think the highest it goes up to is 700 or 800 C, but it can go all the way down to near liquid nitrogen temperatures. And so by basically being able to do a wide range of mechanical testing under a wide range of temperatures, you can get quite a lot of information about the thermomechanical properties of materials. So whether you're doing polymer studies and you want to look at glass transitions, modulus, stiffness, secondary transition, loss modulus, storage modulus. You can also look at eventually doing a number of tests to determine rheometric properties. So you can correlate that from measurement studies of rheology and other things. You can also do creep studies on this. And a lot of these tests not only work for polymer samples, they work for composites, they work for some metals, they work for glasses, just a number of different things that typically you're not looking to necessarily do failure studies, but you're trying to understand the frequency-dependent response or slow time-dependent response to correlate that to other properties of your materials. Optical microscopy. So this is just one of the optical microscopes here. This is the newest one. It's Keyence optical microscope. Magnification goes from 20x to 2000x. It can do just regular two-dimensional imaging. It has the ability to do some three-dimensional imaging as well by sweeping the working distance of the microscope itself, and you can reconstruct three-dimensional images of it. It has the ability to do polarization of light, so you can get different responses from materials that are, say, under strain, or separate out organic materials from inorganic because they will have different polarized responses. It has the ability to do large area stitching. So basically, if your entire field of view of your sample cannot fit into one 20x magnification image, you can actually stitch, I forget how large it can go to, but basically it can stitch a few dozen of them together and form a representative image of your entire sample surface. You can also do tilt studies. So let's say you wanted to do surface energy measurements, like contact angle interactions of your sample. So you can put the camera at a 90-degree tilt and then look at the sample from that oblique angle, and you can actually see how the fluid interacts with the surface as well. Now we do have a number of other optical microscopes, such as like fluorescent microscopes, some more simplistic stereographic and optical microscopes as well. I think this one here is probably the most advanced. We have another microscope, though, that has a special imaging system for optically tracking particles within a fluid. So typically it's used for trying to analyze flow distributions through networks using that system. So here's some more examples from the Keyence microscope. So this was from the catheter tube and balloon, just looking at the different surfaces. Some of this required using the polarized filter in order to see it. Otherwise, with just optical, everything would look like transparent plastic. And then just getting different information on that as well. So as I said, we've got a wide range of other techniques as well. So some of these are gas interaction measurements. So we've got the system here. This is for determining specific surface area of your sample using a BET test. It also can determine, say, pore size distribution for materials that have relatively high porosity within them. We also have a complementary piece of equipment that can accurately determine volume of irregularly shaped samples, basically just using helium to displace it. And so by getting accurate volumetric measurements and knowing the way you can get accurate density determinations for samples that otherwise may not be amenable to techniques such as like Archimedes' principle in doing water displacement. Glucose lactose analyzer. We've got, this is the induced velocimetry system for looking at particle flow distribution. We've got some microtome systems. We also have an electrochemistry station for doing cyclic voltammetry, amperometry. We use it often for doing corrosion studies, also looking at basically different energy systems like batteries, or doing like analysis of small fuel cells, or trying to determine, even using that electrochemistry system to do voltage and current analysis of circuitry. That can be done as well, depending on what you need, because this also has the capability of doing impedance spectroscopy. We have a Zeidel potential meter, so that's basically trying to determine the interactions of colloidal suspensions and seeing how stable they are. critical point dryer for preparing biological samples. So let's say you've got bacteria or something, you need to safely fix them for doing other microscopy measurements. Fluorescent microscope, I touched on that. A dedicated contact angle meter, so that's separate from the Keon's microscope itself that can be used. And there's just a number of other small supporting pieces of equipment. So if there's anything specific that you need for your research, a lot of times talk to us. It might be something that we have in a corner that's not something heavily advertised, or maybe it's something that we have in one of the other facilities, or we might know one of the other labs on campus around that would have that. Often we happen to know a lot of where these techniques are located. So just some other examples before we wrap up here. So this is a failure analysis project that we did years ago with the Ohio Department of Transportation. So this was a coupling bolt that was out in the fields for one of these structures that basically there was some corrosion that caused some failures. So basically by doing some sample preparation, cutting it into a cross section, and doing some optical and elemental analysis, we're able to see the corrosion byproducts and actually map them and see where that corrosion penetrated into the sample and how it could cause failure. And then a related project is actually another ODOT project where this was an overhead truss on a freeway on-ramp, I believe, that failed rather dramatically. I don't think anyone was injured, but it did fall. And so they wanted to understand where these cracks occurred. So basically we did just aside from doing some more traditional fracture analysis and trying to see where the crack initiated and how it advanced with fatigue, we finally were able to identify where it occurred, and it was basically the welds. And so we did analysis of the individual welds, see not only were there some voids there, but then cracking that formed in between the voids, and understanding is actually how that came to be. So a lot of reverse engineering. That's something that you wouldn't necessarily consider as a laboratory measurement per se. So, but these are all capabilities that you could do here as part of your research as needed. So I'm going to end basically with how do you get to use this equipment? How can you come to use it if it's something that you decide is important for your research? So we have a website there that you can go, and it gives a little more details about what's there. Also, on that site, there's a form that you can download for the new user registration form. Basically, you take that, you talk to your PI, and you confirm what is it that you need, what you want to do, what do you need to be trained on. And then you come, typically you see me or one of the other staff members. So we've got 3 full-time staff here. And basically we'll arrange to get you properly trained on things. If you need assistance doing the measurements, we can do that too. And then once you're properly trained on something, for most of the heavier use equipment, we've got online scheduling systems that you can then start reserving your time and using it as needed. And then we're always willing to help. So if you have any other questions along the way, just let us know. So I think that's all I have. So if you want to go back and revisit anything, I know we've only got about 5 or 10 minutes here, but if there's any questions on anything, I'd be happy to answer them.
Let's thank Corey for the great presentation, and yeah, now would be a great time. We have at least 5 minutes for questions.
Corey, you may have mentioned this, but how do you manage time on various instruments?
So it depends on the nature of the instrument. So for some things that are in very heavy demand, such as our electron microscopes or the X-ray diffraction system, we have systems that the users can reserve chunks of time. And so that they basically make an appointment just like anyone else, and they get a chance to use that. Now, and we also try to keep pretty strict to that. We have a policy to where if you make a reservation, you have 30 minutes of grace period to where you can show up a little late and still use it. But if somebody isn't there on time and they're more than half an hour late, somebody else could come and take their reservation spot. And any time on the instruments that are not reserved, they're basically open use. Those are the first come, first serve. So, and then with some of the equipment, once you're relatively trained and you have sufficient time on the instrument that we've been able to confirm that they are very well versed on it and they're not going to damage it or hurt themselves using the equipment, then certain pieces of equipment, then we can open up for after hours use. And then our normal hours of operation are 8:30 to 5 on business days for the university. But these relatively senior level users, then they can get access to come in on nights or weekends and use some of the equipment for themselves. And it just depends on the equipment. Some of the things that are very, very sensitive and very easy to damage, those are things that we might not want people to use after hours, but some of the more robust and heavier use equipment are absolutely open to those that have kind of reached that level of experience on it. So, and then some equipment that isn't very heavily used, we don't even have reservation systems for it. It's just open for anyone who wants to use. But we do ask for all equipment that people do record. We have written logbooks for everything. And so we have to track that. Some of it's for just internal purposes to know that how often consumables are used, when do we need to do some maintenance. Some equipment, such as the X-ray diffraction system, it's actually governed by state law that we have to have everyone fill out the logbook in its entirety, and we're actually audited by the state once or twice a year to make sure we're in compliance, as well as other X-ray operating facilities on campus.
Corey, this is Adam. So you have a background in physics and chemical engineering, and using all of this equipment and understanding the physical principles behind it takes a lot of training and experience. Is that a typical education path to the type of work that you do, being able to decide what equipment to use, be able to interpret the results from the equipment? So yeah, is that a typical educational path?
I mean, it can definitely be a pathway if somebody wants to go into a career of just pure characterization and understanding. That could be. It also, doing research, something that I found is that it's very multidisciplinary. I mean, just because somebody might go into school or go into grad school thinking that they want to do one thing in particular, ultimately you may end up getting involved in so many other aspects of research that might be complementary or something that at the time may seem even unrelated, and yet some of these analysis techniques and instrumentation that you come across during your experience, you find they may have so many other capabilities. And this is something that we try to remind people about, is that don't think of it as something that is not part of your core research. Think of it as just another skill that you're adding to your skill set, your professional skill set, and it's something that may come in handy someday down the road when you least expect it. In fact, one other thing I should mention is that aside from our 3 full-time staff, we also every year we retain several graduate students as assistants. So basically they help us perform work on projects, they help assist users, they help keep equipment update and maintenance, and it's a competitive award basically that is available to all graduate students within the College of Engineering. And basically by doing that, they might get experience to techniques that otherwise they would have never even considered, let alone had a chance, an opportunity to use within the course of their normal research. I mean, we've had bioengineering students doing mechanical metal failure analysis. We've had electrical engineering students doing high-end chemical spectroscopy work. We've had mechanical engineering students learning how to prepare biological samples for fixation and doing microscopy and other measurements of that. It's just, it gets you a little bit out of your comfort zone, but it lets you realize how much more versatile and how much more appeal you can have in the workforce if you can do more than just one type of operation, one type of mindset.
Yeah, thank you, Corey. Yeah, I agree. Especially at a university, our mission is education and teaching, and getting all that broad experience it can make a huge difference. Um, yeah, and we're all mechanical engineers, but it's good for us to understand these other techniques that are out there and equipment that's regularly used. Um, yeah, I know we have a college meeting that's starting at 2 o'clock. So unless there's any other quick questions, I think this would be a good time to end the seminar for today. And thank you to Corey for presenting what can be done at the CMSC and sharing some of his expertise with us. So thank you, Corey.
Not a problem. And I'll just remind everyone, if they want to talk in more detail, just feel free to stop by. My office is there right in 1496, and pretty much have an open door policy that I'm willing to talk to students or anyone else on anything they need.
All right. Thank you very much, Corey. And yeah, thanks everyone for attending.
Right. Thank you.